Good evening, everyone. Is my mic on? Good evening, everyone. Welcome to this Gresham College lecture with Professor Chris Lintott. My name is Christine Goodfellow. I'm the Academic Program Manager here at Gresham College. And it's my great pleasure to see Conway Hall absolutely full to the rafters. It's lovely. Before we start the lecture, a few housekeeping rules. As you know, there are exits here in case there's a fire alarm going off. Please make your way to the nearest exit. There's one there, one in the middle, and one over here. And outside, there will be colleagues helping you to find the meeting point. After the lecture, we'll have the Q&A. Those of you in the hall, you should have a program with a big QR code at the front. Please do not use the one at the back. Use the big one at the front. You can either scan this and submit your question via Slido. They will pop up on this lovely tablet, and I'll try to keep the questions fair between questions on the Slido tablet from online and in the hall. If you'd like to raise your hand, that can be done as well. There will be two colleagues of mine who will bring you a microphone, so please wait till they bring you the microphone and then ask the question. Those of you who are joining us online, same procedure. On the bottom right corner, there should be a QR code. So throughout the lecture, if you have a question, just scan the code and we'll collect the questions here. Very happy to have a large group from St. Benedict's School in Ealing here, this time in the front and not on the balcony. Can I get a whoop whoop? See, last time we tried this, and it's okay, next time, proper. Right? We're very happy that you're here. And it's now my great pleasure to introduce our speaker tonight. It's Professor Chris Lintott. Chris is a professor of astrophysics in Oxford University and a research fellow at New College. And he's also the presenter of BBC Sky at Night, which probably you all know. And he's the 39th Gresham Professor for Astronomy. Tonight's lecture is Alien Earths, What Makes Us Special, and it's the third in the series of the State of the Universe series. So please help me welcome Professor Chris Lintott.
Hello, everyone. Thank you for coming. Thank you for joining us online. When people write the history of astronomy in decades or centuries or even millennia to come, what they'll say about our time, the period that we're living in, is that it was when we got to know the planets of the galaxy, when we swapped from only having our solar system to study to a remarkable diversity of systems spread out throughout our cosmic neighborhood. And that's what this lecture is about. I can even show you some of these planets. This is an image of the star HR 8799, taken with the Very Large Telescope in Chile. It's a real name. And actually, here the light from the star has been removed by an instrument called a coronagraph that hides the light from the star so that you can see those blobs around the edge. And if you look over the course of several years, then you can see that 4 of those blobs move. They orbit around the star. And this is real data showing a solar system in action, not an animation, not something that's made up in a computer, but we're actually watching 4 planets move around the star, a slightly blown up version of the outer parts of our solar system around a star 130 light years away. We now know, though we can see this one because it's relatively close and because the planets are young enough that they glow brightly, and because the star is faint enough that we can play this trick of hiding its light. We now know that when you look at the night sky, almost all the stars in our galaxy likely have planets going around them. The physics and the chemistry that assembled our solar system acted elsewhere, and the universe likes making planets. We know specifically of 6,087 planets, as of this morning, are in the catalogue, and that number is increasing rapidly. This is the discovery with time since the first of these extrasolar or exoplanets was found in 1995. You can see that the number has been increasing dramatically. And as I'll say at the end of this lecture, there's a good chance that by the end of this year, or at least at the start of next year, we'll hit our 10,000th known planet, and we'll have a proper census of what exists in the cosmos. And so it's a good time to think about how our solar system sits in relation to these many different systems and to really reflect on our position in the cosmos. But this lecture couldn't be anything other than poorly timed, because whenever I sat down to write it, there was another discovery of another planet that happened. So last week, for example, we saw this thing. Now, there are a lot of artists' impressions in this talk, because although I showed you those blobs in orbit, it's rare to see these planets directly. So I've labeled them. Mostly, artists make these things look slightly mysterious, like a low-budget 60s sci-fi movie. So don't take them too seriously. But this is a world which NASA promoted as an ice-cold Earth. It's called HD 137010b. And I'll say up front that another running theme this evening is going to be that we're bad at naming things. There has been actually an effort to give these exoplanets proper names drawn from mythologies from many different cultures, and no one uses the proper names. We call them by catalogue numbers. So I will do that tonight. This is HD 137010b, and it hit the news because it's Earth-sized, though cold. It orbits a star that's much fainter than the sun, so probably, though we're not sure, it's maybe about minus 90 degrees on the surface. And the reason that people got excited about this planet in particular, and the reason I had to put it into the talk, was because of its status within those 6,087 planets that we found. Here they all are. This is a plot from this morning. And the higher a dot is on this diagram, the bigger the planet. So Earth's live down at the bottom, Jupiter's at the top. And then you've got the period, how long it takes the planet to go around the star. So obviously for the Earth, which I can circle there, that's 365 and a bit days. That's the length of our year. But you can see for most of the planets that we know so far, they go around much faster. Now this new candidate, I should say there's Earth. Here are the rest of the planets of our solar system. That's the 8, excluding Pluto. If you want to fight me about Pluto, the last lecture of this year's series is about why Pluto isn't a planet, so we'll get back to that. But this new planet is, if it's real, and it needs to be confirmed, it's only a planet candidate, HD 130710b is as close to Earth-like as we found. So it's in this little box somewhere. So it's about Earth-sized, and it has a year that's almost the same as ours. And so this was hailed as a very exciting discovery. The goal of most of the planet hunting efforts have been to get closer and closer to worlds that look like ours, because if we can find these alien Earths, we can start to think about life in the cosmos and think of these planets as home for life. And we could certainly do that. I could give that lecture, but I think it's unfair to other planets. For example, my friend Hannah Wakeford, who's an exoplanet expert in Bristol, one of her favourite planets is HD 189733b, artist's impression. This one's blue and a bit scary. The blue is real, it is slightly bluish. This is a giant planet like Jupiter, but it's puffed up. And it's puffed up because it's very close to its parent star. In fact, it's so close to its parent star that its temperature is likely in the thousands of degrees. It has winds that blow at more than 5,000 miles per hour. That's about 2 kilometers per second from the hot side to the dark side. And it rains on this planet shards of glass sideways because of the wind. And I think what I want to get across tonight is that's as exciting a discovery as another poxy little Earth that's a bit like this one, right? We might, in fact, learn more from a planet unlike anything we'd ever dreamt of than we do from finding other Earths. The great Richard Feynman, the physicist, thinking about how we write about science, said, "What men are poets? If Jupiter be a man, they sing, but if he be an immense spinning ball of hydrogen and ammonia, stay silent." I think it's probably because it's hard to rhyme with ammonia. But, what sort of scientists are we? If the galaxy's filled with copies of our solar system, we feel satisfied. But if it's full of weird planets where it rains glass sideways, we feel disappointed. We need to embrace the fact that we're finding alien worlds. And the reason that's hard is that for hundreds of years, we had our solar system to study. And so we got the idea that it was normal. So I love, for example, this painting. This is Joseph Wright of Derby's painting, a philosopher lecturing on the orrery, which is currently just down the road in the National Gallery. It's an 18th century painting, As you can see, there's an astronomer lecturing and some of the audience are listening, so that's nice. But the model of the solar system that's being presented here really echoes down the centuries to today. We think of a solar system as having a single star at the center, planets in a disk, so they're all coplanar, in roughly circular orbits, and within that solar system there's an order. There are two types of planets. There are rocky planets like the Earth, there are gaseous giants like Jupiter, and they're organized so that the rocky planets are close to the Sun, Mercury, Venus, Earth, and Mars, and then the gaseous planets are further out. Jupiter, Saturn, Uranus, and Neptune are further out. So we have an order. And then on top of that, Earth is about the right distance from the Sun in what used to be called the Goldilocks zone, but is often now called the habitable zone because people have no fun, where the temperature is just right. Planets in the habitable zone are suitable homes for our kind of life. That model makes sense. We know, for example, that planets form in disks of material that are left over once stars collapse under their own gravity and begin to form. So on the left here is an artist's impression of what's called a protoplanetary disk. You've got a young star in the middle, you've got a pancake-like disk of material that's clumping together to form planets. On the right is a real observation. This is of a newly formed star called HH30. The red bit is a jet of material that's being ejected by the young star's magnetic fields. The green bit is leftover material, but that hamburger-like bit, that dark line through the middle, that's that protoplanetary disk seen here edge on. And within that disk, planets are forming. These things are common. This is a visualization of my favorite object, the Orion Nebula, a nearby star-forming region. And this is using real data from the Hubble Space Telescope. But as we zoom in, we see the young stars, but we also see objects called propylids. These are stars that are enshrouded in dust. Think small sand grain-like particles. There's one just going past there. And within those propylids, we see evidence for these disks. And the fact that it's a disk and a pancake, of course, explains naturally why all the planets in our solar system lie more or less in the same plane. If you form things out of a disk like you see here, then you end up with that. And so the model of the orrery, the model of the solar system in Joseph Wright's painting, is actually pretty good. The fact that you have the rocky planets close to the star and the gaseous ones further out can be simply explained by temperature. Within a protoplanetary disk, if you're near the star, you're warmer than if you're further out. And so if you're near the star, hydrogen gas will evaporate, will be heated and expelled. So that means where you form a planet near to the star, you form the rocky bit through dust grains sticking together in a process that we think we more or less understand, though the details are hazy, and you get a nice rocky planet, and that's it. If you form a planet further out, you get to the point where you're the size of, say, Mars, and you have enough gravity to quickly pick up the gas that's lurking in the outer disk, and you grow quickly to be a gas giant like Jupiter. And so we can explain the features of our solar system using some fairly basic astrophysics. And so therefore it's surprising that when we started to find planets, these rules that I set out don't apply. And this was clear really early on. The first extrasolar planet discovered back in 1995 was a planet called 51 Pegasi b, or 51 Peg b to its friends. And this was a giant planet, bigger than Jupiter, that goes round its star in just a few days. So it's much closer to its star than Mercury is to the Sun. It's the first of what we've come to call hot Jupiters, a new class of planet that we didn't expect to exist. And in fact, it's a good job it did exist because it made it easier to find. We don't see most of these planets directly, and 51 Peg b was found using a technique called radial velocity. And this draws on a principle, which is that gravity acts two ways. So we're used to talking about, say, the Earth orbiting the Sun. But actually, planets and stars mutually orbit their center of mass. So what you can see here is in blue, a fairly massive planet in orbit around, say, a sun-like star. But you can see what's actually happening is that the star is moving as well because of the planet's gravity. If all you could see was the star, then what you'd see is the star wobbling towards you and away from you, and towards you and away from you. And using the spectrum of the star, its light split up into the rainbow in the bottom right, and using the features of the stellar atmosphere, these dark lines, what we see is that they move to the red and to the blue and to the red and to the blue with a Doppler shift that betrays the velocity of the planet. So if you can stare closely at the spectrum of the star, you can pick up these periodic motions and deduce that the planet must be there. And because this is gravity, the bigger the planet, or rather the more massive the planet, and the closer it is to the star, the bigger this shift is. For 51 Peg B, the shift in the star's motion was about 70 meters per second. These days, new experiments get us down to being sensitive to maybe a meter per second, something like walking speed. So these are incredibly precise measurements, but they were able to find 51 Peg because it produced a relatively large change in the star's motion. And so immediately, as soon as this result was published, people questioned the existence of this planet. This wasn't what we thought we were going to find. Remember, we thought we were looking for clones of our solar system. Jupiter-like planets should be out in the outer solar system. We still believe that Jupiter-like planets form in the outer solar system. That logic that I told you about, in which you need the gas that's all the way out here to accrete onto the newly formed planet, that still holds. But we think that unlike the old picture, where planets form and they stay put, what we think happens is that planets migrate through the disk of material in which they're forming. We can even see this happening. This is an image from a telescope working in the microwave region of the spectrum, so very short-wave radio waves, a telescope called ALMA up in the Chilean Atacama Desert of a system called HD 169142. And what you're seeing here is a series of rings around a young star. And to give you a scale, the dotted line there is our solar system. So this is quite a large-scale system. And what you can see is those rings are being shaped, particularly the two outer ones, are being shaped because something the mass of 10 times the Earth, a large planet, is moving within the disk, it's hoovering up dust, and it's creating these resonant patterns, these rings, which tell us also that the planet is migrating inwards. And so we think in many of these systems, and we see patterns like this in many different ALMA observations of many different protoplanetary disks. There are 3 examples of relatively nearby stars here, and we're looking deep down within the first few 100 million miles around each of these stars. We can see that giant planets are forming, and because of friction with the disk, they lose energy and they migrate inwards. This is something that it turns out we should have suspected happens. When you run a computer model of a disk such as this, and you put a giant planet in it, as it accretes material, you'll find it will move inwards until such a time as it ends up in a place where there's no material, until it runs out of fuel, if you like, to move inwards. And so just from this one system, plus the ALMA observations, we've suddenly got a different question about our own solar system. It's not that we should expect giant planets in the outer parts of these different planetary systems. What we should ask is why our giant planets, Jupiter, Saturn, Uranus, and Neptune, seen here in recent images from the JWST, we should ask why these giant planets didn't move inwards and crash through the space where the Earth is and destroy any chance of having our nice rocky planets close to the star. And we still don't know the answer to this. We think we know. It's a story for a lecture next year. We think that these planets did move around. It's possible that Uranus and Neptune swapped positions early in the solar system's history, and Jupiter and Saturn seem to have moved outwards as well, causing chaos for some of the smaller bodies of the solar system, but they didn't come crashing through the inner solar system. And we still don't quite understand why that's the case. One possibility is that we got lucky from an Earth perspective because both Jupiter and Saturn exist. And with 2 giant planets, it's possible the dust got consumed, it got hoovered up fast enough that migration wasn't effective, and that you ended up with giant planets stranded in the outer part of their solar system. But still, that's a lot to build on one planet. In 1995, we just had 51 Pegasi b, but you know that we found many, many more. And in fact, if you looked carefully at that graph that I showed you, this one, then you can see there are jumps here, particularly in 2014 and in 2016. And those jumps are because of one mission, a planet-hunting spacecraft called Kepler, which was launched in 2011. And Kepler is an amazing mission. It's not a big telescope. Doesn't need to be, but it did an extraordinary thing because of the extraordinary people who ran it. The principal investigator was a scientist called Bill Barucki, who I think possibly wins the prize for the most perseverance of anyone that I've ever met. The first conference of his team thinking about whether they could build a telescope to find planets around other stars was in 1984. In 1992, they put in their first proposal to NASA, which was called FREZIP, standing for Frequency of Earth-Sized Inner Planets. Terrible name. They also didn't have good enough cameras to convince anyone that they could do what they wanted to do. They tried again in 1994. They now had good enough cameras, but they were too expensive. So they did a load of lab work to show that the cameras were good enough. In 1996, they were told that the data processing was too difficult. They built a version in the lab to show that they could do that. In 1998, they applied again and were told that it would never work when it was in orbit. So they built a model which they could shake to simulate the rocket launch, show that it still worked, and in 2000 they were selected for study. In 2001 the mission was picked, and 10 years later they got to fly their mission. And in that time, 2 other people had found 51 Peg B and won the Nobel Prize for finding the first exoplanet. But Kepler really, really was revolutionary because it did my favorite thing in all of observational astronomy. It did a simple thing really well. It stared for 3 years at one patch of sky in the constellation of Cygnus. And it looked at the brightness of all the stars in that patch of sky, a few 100,000 of them. And what it looked for was a dip in brightness. Just a small, maybe less than 1%. Of the star. And the reason that matters is that's a way of indirectly finding a planet. Here is a video of the sun on a particular day in 2012 when Venus, as seen from Earth, passed in front of the sun. These transits of Venus, because of the way the orbital mechanics work out, are actually rather rare. The next one won't be until the 22nd century, but we have it on video. And on the left is the video, and on the right is the physicist's view. The right is a graph taken, this is from a beach in Queensland, if I remember correctly. This is what happens when you take the kind of meter you use to measure light in a school lab out. And this is just the brightness of sunlight. And the important scientific result here is that when Venus is in front of the sun is slightly dimmer. So this isn't rocket science. When I put something in front of a star, it gets fainter. Fine. But if all you had is the graph, you could infer that the planet was there. Particularly if you saw a repeated pattern of dips, you could deduce that the planet was there. You get its size, because you know how big the dip is. And you also get the period, because you know how long it takes between dips. And because Kepler was capable of looking at hundreds of thousands of stars at once, even though you have to be lucky for a planet to get in front of its star, Kepler got lucky again and again and again. It produced our first proper census of planets. And there were more surprises in store. In fact, even if we just look at the size of the planets that it found, and here's me demonstrating this. This is Stargazing Live. This is Brian Cox's program. This is a crude bar chart that I put together. Trying to buy that many gobstoppers in rural Australia was actually a problem, and that's another story. But on the left in yellow, we have the proportion of the planets that are Earth-sized. In green, we've got the proportion of planets that are sort of Uranus and Neptune-sized, and in blue, the proportion that are Jupiter-sized or bigger. So you can see that actually, even though the first planets we found were hot Jupiters, they're actually rather rare. We found them because they're easy to find. And though they do exist in the universe, they're not the most common type of solar system. I skipped over orange. In orange are planets which are the size of what have become known as super-Earths, but you can really think of them as mini-Neptunes. Things that sit between about 2 times the size of the Earth and about 4 times the size of the Earth. These are the most common type of planet in the galaxy. And we don't even have one in our solar system. And so if you just studied us, you'd never know that these things were out there. As an example, there's a planet called Gliese 581c, which, when it was discovered, caused a great deal of excitement because it was sort of only a bit bigger than Earth, and it was in that Goldilocks zone. It was the right distance from the sun that you might think it would have conditions that were suitable for life. Now, this doesn't even have an artist's impression. This is the range of radii that it might have. But the thing is, these things, if all we've got is a dip in the brightness of a star, it's very hard to work out what these things could actually be. It's possible that this planet is a big rocky world, so sort of like literally a super Earth, maybe made of silica or something like that. It's possible this world is what people call a cannonball planet. It could be solid iron, sort of the core of what we would recognize as a terrestrial planet. It could be a dwarf Neptune or Uranus, sort of a Jupiter but shrunk down. It could be, we think, a diamond world, carbon-rich, of unusual composition. People have even proposed there's a thing of being able to have hot ice. If you have an ocean that's deep on one of these worlds, by the time you get to the bottom of the ocean, it's possible that the water is under such pressure it becomes solid, but without being cold. So you could drift down in the ocean if you could avoid yourself being crushed. You drift down and you'd end up in a solid sea floor made of this unusual hot ice. Or it may just be a blob of carbon monoxide. We don't know what these things are. But we know that they're the most common type of planet in the galaxy. And I think we'll find out as we study more of them in more detail that all of the things I've just listed exist in different proportions, and none of them exist within our solar system. We can do science with what we do know. We know the size of these things from Kepler. And one of the fun results is that this is the proportion of planets of different sizes. So this is the number of planets that we think exist per 100 stars of different sizes relative to Earth. And I think you can see that there's a gap there between about 1.5 and about 2 Earth radii. There's this gap. So things are either smaller or larger than that, and not so much at that particular volume. So that's interesting. What kind of physical process can produce this change in radii? It causes a split, if you like, in the family tree of exoplanets, so that we have super-Earths and mini-Neptunes as separate things. Well, one possibility is that this is telling us about how these planets form and assemble. We know that in the protoplanetary disk, you start off by sticking dust grains together. This process continues until you get something that's large enough that it can start to accrete gas. And it may be that the distinction between whether you end up as a rocky super-Earth or a gaseous mini-Neptune, maybe that distinction is to do with how fast you can assemble. Because if you can produce quite a large rocky core early on, like the planets at the top of the schematic, then you quickly accrete gas and you grow to be a respectable mini-Neptune. But while this is happening, the star is heating up. Young stars limit the lifetime of the disk that surrounds them. As they heat up, they blow away the gas and the other material. And so you're in a race against the star to gain your atmosphere if you're a newly born planet. And so if you're slow, perhaps because the disk is less dense, there's less material, or maybe the composition makes a difference, or maybe you're just unlucky because there's a larger planet further out, then what happens is that you grow to the point where you're able to accrete gas just at the point where the star heats the disk. And then you end up on the other side of this divide as a super-Earth. So we're learning about the influence of the star on the planets from these unusual worlds. And again, this is not a study we can do in our solar system. This process didn't occur here. Speaking of losing atmospheres, I think this is mostly for fun because they're my favorite type of planet, so I don't think they quite fit the story, but they were also unexpected. The poster child for the next type of planet is TOI 561b, found by Kepler's successor mission, TESS. TOI 561b, again in an artist's impression. This is the distant view. If we zoom in, you can see it's got that classic artist's impression murkiness to show that we don't know what's going on the surface. But you may get the impression from this is what's known as a lava world. This is a world that's small enough that it's probably rocky, and that it's close in to the star. In fact, this one goes around the star in, again, just a few days. As a result, its surface must almost certainly be molten lava. And we do not know how to form these things. One possibility is that this is what an old hot Jupiter looks like. Because if you put a Jupiter close enough to the star and heat it over millions or even billions of years, the atmosphere will very slowly boil away. And you may end up with the core of your original planet scorched and orbiting around the star. These are complex worlds with stories to tell us. Just the other week, we got our first study of the atmosphere of one of these things, in fact, of this particular star. This is from the JWST. And here's the spectrum, and the white bits are the measurements. So that's how bright the planet is in different wavelengths of light, and this is all in the infrared. And the only thing to take away from the squiggles, really, is that if this thing was just bare rock, we'd expect it to reflect the stars like the white line there. And if you have a bare rock and then you put a thin atmosphere, you get the purple line. And if you put a big, thick atmosphere with lots of molecules in, you get the yellow line. And the yellow line is closer to the white points than the other two. And so this world seems to have a thick atmosphere. It's an atmosphere that, if the models are right, is mostly made of carbon, of things like C2, carbon molecules. And we don't know how to form them. And we don't know how to form them in conditions that we expect to exist on this planet. So there may be activity on this world that's promoting this atmosphere, that's producing it continuously, with other elements like oxygen and nitrogen kept lower down in the atmosphere. This one planet is keeping teams of people busy trying to understand chemistry that we never dreamt existed. So how are we doing with our orrery so far? So the idea of ordered rocky and gaseous planets is gone, but we do still have planets mostly in circular orbits, and they're mostly around single stars. So let's destroy those things next. Let's start with what planets can orbit. Actually, I hope I was careful earlier in the talk when I said the first planet around a normal star was discovered in 1995. Because in 1992, we found planets around a pulsar. Now, for those not familiar, a pulsar is the remnant of a massive star that's exploded in a supernova. It's the core of the massive star, maybe the size of the Earth or something like that. And these are rapidly rotating things with strong magnetic fields that produce lighthouse-like beams of high-energy radiation that whiz round. And we see them from Earth when we happen to lie in the part of the galaxy that these beams sweep across several thousand times a second in some cases. So we see them pulsing in the radio. They're interesting objects for all sorts of reasons. And there's a game of trying to measure the timing of the pulses really carefully for all sorts of reasons. I mentioned it last year when I was talking about trying to think about black holes in the galaxy. But for a small number of pulsars, including this one, which is PSR J32222650, for those making notes, we see there's a slight change in the pulse frequency, and it's periodic. So what that means is the pulsar's moving towards and away from us very slowly. And the inference is that there is a planet in orbit around the star. And this is obviously a computer animation of that. And it's not that it's a terrible computer animation, it's that we think this planet is so close to this massive object, which has very strong gravity, because although it's only the size of the Earth, it weighs much more than the Earth does. A teaspoon would weigh several billion tons. This planet must be lemon-shaped, because it's distorted by the pulsar, and it will always keep the same face pointing towards the pulsar. It, too, we now know, as of last year, through studies with JWST, has an atmosphere. It's got hydrogen and carbon in its atmosphere. And we're not sure what to think about this thing. Is it a survivor? Is this a planet that existed before its central star exploded and ended its life to produce the pulsar? Is this something that assembled in a second wave of planet formation after the supernova? Or is this perhaps just a captured object that was wandering by? We're not sure, but there are a handful of pulsars that have these things. Most pulsars do not, but planets exist even here. And in fact, while we're talking about star death, even sun-like stars, which don't produce anything as dramatic as a pulsar, but will produce a white dwarf, the faint remnant, the core of a sun-like star, which will fade away. We've seen white dwarfs with debris around them. This is an artist's impression of LSPM J0207 plus 331. This is an old white dwarf which has a disk of material surrounding it. and it's polluted by the remnants of planets. So planets seem to be able to survive. Now, I said in the orrery, we have circular orbits and a single star. Those turn out not to be universal features either. This is HR 5183b. This is the Whiplash planet. It says a 3 Jupiter mass planet on an orbit around a star that swings it from roughly where Jupiter is in our solar system all the way out to roughly where Neptune is in our solar system. So this is a realistic description of its orbit. We don't know how to form anything like that. We think we know how to form planets on circular orbits, but we've no idea what's happened here. One possibility is that there were other planets in the system, and they were ejected, and in that ejection, we've ended up with a very elliptical orbit for this particular planet. So we can't assume that planets are circular, and nor can we assume that they're around single stars. I'm a big fan of this illustration, which is from the Economist coverage of 2 planet discoveries about a decade ago. And in particular, on the right, you have a representation of a planet called PH1b, which is a Saturn-sized world in a circumbinary system. So you have 2 stars going around each other, and you have this planet going around both of those stars. So it will have sunrises of 2 stars on this planet, except that it's also in a 4-star system. So you have another pair of stars that orbits the whole thing. And somehow, in this environment, we've managed to set up a disk, the universe has managed to set up a disk of material that lasted long enough to form a planet despite being disrupted by these 4 stars. So you can't assume that only single stars have planets. This one, by the way, the reason it's PH1b is that it's Planet Hunters 1b. This was discovered not by professional astronomers, but by volunteers on a website called Planet Hunters, which the team that I run maintain. And if you fancy finding a planet, then we have new data up at planethunters.org from that test satellite, the successor to Kepler. And we have thousands of people helping us look for those dips in brightness that reveal the presence of planets. And it's a great joy every so often to be able to email people and say, do you remember visiting that website? Well, you found a planet. It's really quite something that we've gone in 30 years from Nobel Prize-winning discovery to something you can do on a computer in your lunch break. When I said this area was moving fast, I really, really meant it. The final and weirdest type of planet I think I want to mention are very unusual indeed. They're found by a different technique, still used by Kepler. So if you imagine Kepler staring at a distant star, and imagine a planet traveling through the galaxy from left to right here, what happens when it comes between us and the star? Yes, it might block out the light from the star, but because the planet has gravity, and because Einstein's theory of relativity tells us that gravity bends light, at that moment when it's exactly in line, it actually lenses the light from the distant star. The planet's gravity acts like a telescope lens, and it magnifies the distant star. So what we see is in the graph in the bottom right, that you see a sudden rise in brightness and a drop that's symmetrical and distinctive. You can look in the Kepler data for stars that follow this pattern. And people have been doing this for a while, partly because free-floating planets in the galaxy were proposed at one point to be a candidate for the dark matter that we know makes up most of the galaxy. Turns out there aren't enough of them for that to be true. But we know of lots of free-floating planets like this one. This is Ogle 2016 BLG 1928. The names are getting more absurd. This is a Mars-sized planet, maybe, or a Mars-mass planet, something thrown out of a solar system and traveling amongst the stars. And we think that there are something like 200 billion such planets in the Milky Way. In other words, the most common type of planet in the galaxy may not even orbit a star. It may, in fact, be a free-floating planet, lost and dark between the stars. We're a long way from thinking that our solar system is the only template. And we're about to make more progress. I mentioned at the beginning that in the next year or so, we'll find our 10,000th planet. Remember, we're only on 6,080, was it 3, so far, as of this morning. And the reason that's true is because of this satellite. This is Gaia, and I devoted a whole lecture to Gaia last year. Gaia is our celestial cartographer. It's the European Space Agency's mapper of the stars. And it has a new data release coming out this year, which will include for the first time measurements of how the stars have been moving in the sky. So not just their positions, but how the map of stars in the sky has changed over time, over the last 15 years or so. And the reason that matters is if you look on the right, is because as we saw before, when a planet orbits a star moves. Now, until now, we've been picking this up by looking at the spectrum of the star. And so we've been sensitive to planets that are very close to the star. But actually, even more distant planets can affect a star's motion. On the left is a sort of 50-year diagram of the movement of the sun, pulled mostly by Jupiter. And it's not much, but the sun does move around its center of mass as Jupiter and to some extent Saturn orbit it. You can use this sort of thing to rule out the presence of a very large planet in the outer solar system, for example. And so Gaia will be sensitive not to planets that are near its star, but to large planets, Jupiter-like planets, on Jupiter-like orbits. And the prediction from the literature is that in this data release that comes out later this year, there should be evidence for about 7,000 of these things, assuming that our solar system is a good model. So who knows how many we'll find. And we may find that these things are much more common, that our solar system is indeed typical that it has Jupiter and Saturn and large planets. Or we may find that these things are rare. We don't know, but we're about to find out towards the end of the year. And so with this cavalcade of planets, the set of alien Earths, these exotic worlds that have glass winds and strange orbits and unusual properties and hot ice and all the rest of it, it's interesting to come back to thinking about our world. And I can't resist showing you, I think this was an April Fool's paper, but it was fun. So this took data from TESS, the satellite that's been discovering planets for the last few years. And TESS is on an elliptical orbit around the Earth. So the amount of background light it gets from the Earth changes. And so this team took that background light and put it through the kind of processing that you'd use to try and understand what a distant planet was like. And then this is the map that they got of the Earth from that data. Not the line bits, that's obviously added later, but the dark and bright bits. And they say, due to the low resolution of the map, bright features, which we'll refer to as South America, Africa, and Asia, are associated with two dark features, the Pacific and Atlantic. So you'd get the idea that there are continents. And then what the authors do in this paper is they get one of their 7-year-old sons to draw the planet that this data describes. And here we are. So this is the Earth as seen as an exoplanet, and part of this context of these very different worlds. And it seems likely, people have spent a lot of time arguing, that there will be Earth-like planets, things about our size, things about our distance from a sun-like star, in the data set, in the tens of thousands of planets that we will collect. And it may be that the planet I started with, HD 1307010b, that might be an Earth-like planet. But in the context of this diversity of worlds, it feels really strange to worry too much about Earth-like planets. It's like deciding that you're really interested in the cornucopia of species in the natural world, and then deciding you're only going to study places that look like Hyde Park. Right? Not only is that a terrible way to do science, it makes for very poor David Attenborough documentaries if he's always in Hyde Park, although if anyone can do it, Attenborough probably can. And so what I want to tell you to do when you look in the news in the next few years and you hear again that astronomers have found a planet that, please be open to the fact that they're not all Earth-like, that we have this diversity. And I found Alex Ho is an astronomer in the States who took an old idea, which Alex Delgado and others have pushed over the years, and has categorized all of the planets. And he made these exoplanet orreries. So we could show you the diversity of systems. We can, in fact, let them scroll past. So the bottom left, we're going to add in all the planet systems where we only know of one planet, and then we'll get the 2 and 3 planet and more systems over on the right. And amongst these systems, as they scroll past, there are hot Jupiters, hot Neptunes, warm Jupiters, warm Neptunes, lava worlds, undoubtedly Earth-like planets, Venus-like planets, planets that behave like comets, those with stripped cores, a few diamond planets, There are planets around young stars. There are planets around old stars. Said planets around pulsars, which don't make any sense. Planets around double stars that orbit both of them. Planets around double stars that orbit a single star. There's planets in 3-star systems. There's one planet so far in a 4-star system. That's ours. You've got planets on their own. But we also know systems where there are more planets than the solar systems. There are sub-Saturn, sub-Neptune, super-Earth, sub-Earth, super-Jupiters, super-Puffs. That's a real thing. Super-Mercuries, planets on elliptical orbits, perpendicular orbits, sideways planets, tidally locked planets, planets on resonant orbits, hazy planets, planets with clear atmospheres, planets where it rains glass. There's a planet where it rains iron as well. There are cloudy planets. There are planets with rings. There's a giant planet that has a Neptune-sized moon, maybe. There are free-floating planets, the planets in protoplanetary disks, in the thin disk of the galaxy, in the thick disk of the galaxy, in the halo. We've even got extragalactic planets. Icy planets, ocean worlds, water worlds, things called Hycean worlds that are controversial. Tidally locked worlds, smashed up planets, egg-shaped planets, and my dear exoplanetary colleagues have named eyeball planets, popcorn planets, candy floss planets, and marshmallow planets amongst the things. And my point is that thinking about these things teaches us more about physics. Joseph Addison, things we started with the 18th century. Joseph Addison wrote in 1712, thinking about our solar system, that contemplating planets means that we're filled with a pleasing astonishment to see so many worlds hanging one above another and sliding around their axles in such an amazing pomp and solemnity that our imagination finds its capacity filled with so immense a prospect and puts itself upon the stretch to comprehend it. When they write the history of astronomy in decades or centuries to come, they'll notice that this was the point where we had to stretch ourselves to understand quite how wondrous and varied the planet population of the galaxy are. Thank you very much. Thank you.
Adding circles again.
Yes, indeed.
So we've got time for questions now. There's 2 colleagues at the back of the hall with microphones, and also if you want to scan this in the hall or if you want to scan the QR code online, please do so. We've already got quite a lot of questions here online, but maybe let's start with a question from the hall. There's one here at the front. Just 1 second.
Microphone is on its way in a non-circular orbit.
How did Earth get its atmosphere? Because it isn't hydrogen or helium primarily.
Yeah, really good question. So we don't think it's an original atmosphere. So we think that when Earth formed, it was so hot it would have been a rocky body. And all the volatiles, so that's the gas and the water that we drink and so on, we think came later. So the best theory is that the Earth was bombarded by a huge number of comets and asteroids early in its history, and they brought ice from the outer solar system. So one of the things that we're learning about the start of the solar system, it was a chaotic place. There were maybe 20 things the size of Mars knocking around the inner solar system and colliding and causing things to change orbit. And so we lived through this period where we were bombarded, and that's where all of that atmospheric material came from. The details of that we don't understand yet. And so one of the reasons people are sending probes to comets and asteroids is to see whether the composition matches and see whether there's a reservoir out there that can supply our atmosphere and our water. But we got it afterwards.
Okay, question online from Teresa. Do you think hot Jupiters are rare because most of them have already evaporated into much smaller cores, such as Mercury might be, which are harder to detect?
Yeah, less so Mercury, but the lava worlds might be the leftovers of hot Jupiters. It's also the case that we're not really sure how to stop these things if they're migrating inwards. So if you have a disk of material and then a gap, they get to the edge of the disk and maybe they stop. But it's possible that they plunge into the star. So it may be that the hot Jupiters are rare, not because migration is rare, but because surviving is hard. So the details of that need work out. Studying the things we're seeing with ALMA, where we see this process in motion in these disks, I think will help us understand that.
Mm-hmm. Another question from the hall, maybe? There's one here in the middle, the gentleman in the grey jumper.
There's another one down here, which maybe we'll take next.
Thank you.
Yeah, you briefly mentioned one exomoon, I think.
Yes.
And so given how, in our solar system, how fascinating the moons are, what's the prospect for being able to study moons in other parts of the
Yeah,
galaxy?
there's a lot of interest in that, partly because exomoons are cool, but also because if you care about life, then you can make arguments that the moon has done a lot for Earth. It keeps our axis stable and perhaps takes some of the flak of incoming asteroids from us. So people would like to know whether exomoons are common. It's tricky, though, because all of these indirect methods, imagine a transit method where you have a planet going in front of the star. Imagine every time that happens, the moon is at a random point of its orbit, and so it's very hard to pick out the signal of the moon. So far, no luck with this one exception. There's a Jupiter-sized planet that's got a distant Neptune-sized thing that seems to be going around it. So if the data works out and you think something Neptune-sized can be a moon, then we've got one. The nice thing, if it is real, the way the system's set up is it would be possible for that Neptune-sized thing to have moons, which would be the moon of a moon, which in astronomy is called a moon, which is just my favorite word. So I hope we find exomoons, but also I think moons would be great as well.
Angela, there were two gentlemen here at the front. Could you just bring your hands up again? Yeah, thank you.
So if you did, if you make Earth a lot bigger, would you still be able to live on it, even though the gravity would be much stronger?
Yeah, this is a big argument with these super Earths. So I think it depends how much bigger you get, but given that we don't really know what conditions life really needs, I think you're okay. The trick is the trouble is that the atmosphere is really important, right? Because people say Earth is in the habitable zone, right? We're the right distance from the star, so the temperature's just right, so our kind liquid water can exist, our kind of life can exist, and that's true. But the moon is also the right distance from the star. And you don't want to exist on the surface of the moon without a spacesuit, trust me. And so the atmospheres really matter. So I think the bit we don't understand is if you make the Earth larger to one of these super Earths, what kind of atmospheres can they have? And then what temperature do you get underneath that atmosphere? So that's the next question. I think the gravity, I don't know, maybe we just have really flat elephants or something, but I'm less worried about that than I am about getting the right temperature.
Thank you. One online. In what ways is AI helping you find more and bigger varieties of planets?
It's interesting. So this should be a problem that AI can attack. So especially when you're looking for these blips, these dips in material, dips in brightness rather, you're looking for a repeated pattern in a noisy signal. So machine learning should be able to help. I've worked on that with some of my students, so have other people, and it does okay, but we still find that because the signal is so noisy, and because we care about planets where we may only have seen one or two transits, it's still worth looking at the data. So machine learning gets us somewhere, but one of the problems is you need training data for modern machine learning, and we'd like to train it by putting simulated planets in, but what we actually tend to find is that the machine learning is better at guessing whether that's a simulation or not. So tricking the machine in a convincing way is hard.
Mm-hmm. Do we have more questions from the hall? Maybe from this side? Yeah, could we bring the microphone here? And then there was one over there. Okay.
Hello, Adi. What's the nearest exoplanet they've discovered to us?
So we know that our nearest star, Proxima Centauri, has at least one world going around it. And so people are very excited to discover whether that might be part of a larger system with more planets or whether it may be suitable for life, because people are interested in that. What we'd really like to do is to be able to study that with a picture, because it was discovered through one of these indirect methods. And there's a great, slightly speculative idea where you take a space telescope, you put it on the edge of the solar system, you line it up, so you've got your telescope, you have the sun, and then you have Proxima Centauri, and then you can use the sun as a gravitational lens and magnify an image of a planet. Then you might get a blurry image of the planet. So maybe we'll do that someday. Yeah, so that's the nearest one. But because we have to get lucky in that the planets have to be in line so that they get in front of the star, or they have to line up so that we get a radial velocity signal, we think almost all stars seem to have planets because we keep getting lucky. So I think almost more interesting question is are there stars nearby that don't have planets, and why don't they? But we're not able to attack that one just yet. But yeah, we've got planets next door. Almost every star that's mentioned in any science fiction, Tau Ceti or so on, they all have planets. So science fiction writers now have a selection of worlds to set stories on.
There was one question over here. Yeah, Rachel, thank you.
How rare could two planets orbiting a barycenter, or are they even possible?
So you mean two planets orbiting their own center of mass?
So two of them are orbiting center of mass, so like circumbinary stars?
Yeah. So we see a surprising number of those. We've still got the only 4-star system was discovered by our planet hunters, but we do see quite a lot of circumbinary. So both planets, where there's a binary star and planets going around one star, but also these ones where they go around both, they seem to all be nearly but not quite unstable. So they're about as close as you can get without being thrown out. And so that must be telling us something about how they form. Maybe the disk of material is stirred up by the two stars or something like that. So the details aren't clear, but they seem common. So it may be that it's as common to have a planet in a double star system as it is to be in a single star system. And only about half the stars in the galaxy are in single systems. So this makes a big difference when we're trying to calculate the number of planets in the galaxy. Thanks for the question.
Running out of time, so I'm grouping two people together. Neela and River are asking, how are these hot Jupiters able to stay stable, and why doesn't the gas burn off instantly?
So the key word there is instantly. So we have seen them that behave more like a comet, where we see the gas evaporating away. And that is still a slow process, so over millions or hundreds of millions of years. So they're not so hot that the gas escapes. Remember, they're massive system. We don't see, when we see the smaller worlds, we don't see a thick atmosphere around a smaller world. It's the big, chunky Jupiters. They've got a lot of gravity, and so even at temperatures of thousands of degrees, they can hang on to their atmospheres for a long period of time. But because they're all locked so that they orbit with the same face pointed towards the star, you have a hot side and a cold side, and that's what creates these winds that are really dramatic. And my friends who study how atmospheres work are having great fun trying to understand these very alien worlds.
We're kind of running out of time. I've got a question. Are you absolutely mad to throw a birthday party the day after St. Patrick's Day in your next lecture? Because the next lecture will be the universe's 100th birthday, galactic fireworks and little red dots on the 18th of March.
It'll be fine. Cake for everybody.
You bring, you bake?
Sure, we'll work it out.
Right, we'll talk.
Good.
Okay, right.
Thanks.
So that's the next lecture. But thank you very much for all of your questions. Thank you for coming or watching us online, and thank you very much for this fascinating lecture.
Thank you. Thanks.